So, my talk is named this functionality and layered composites. So I come from Finland. It's far north, as most of you recognize, and the city of Tampere is located there. We have at University of Technology about 1,200 students and about 550 in material science. City of Tampere is summer view, winter, 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 and summer. Okay, that was a fact part, and now I go to fiction mostly. Okay, here is a short content of my talk. There was only these 4 positions given by the organizers, so that's shortly. So first, I speak a bit about the thermally sprayed nanostructured coatings. Thermal spraying is a wide or large industrial branch to prepare coatings for different kind of demanding applications. They can be used to increase wear resistance, corrosion resistance, protection, electrical insulation, and also certain functional properties like which are used, for example, in fuel cells or biomaterials. And there is a large industrial branch where they are used, like automotive industries, aerospace, and the process industries. And in Finland we have a paper and pulp industry, at least so far, and there is a large applications for thermal spraying. If we speak about plasma, if we speak about ceramic coatings, plasma spraying has been the state-of-art technique to produce those coatings, but nowadays there is also these high-velocity spray systems like HOVF spraying, which also can be used for certain ceramic materials. As you have heard during these days, these nanoscale structures are looked to for improved properties and, for example, to improve the wear resistance or biocompatibility, as I will tell you. But it's not so simple actually to produce nanostructures by thermal spraying. And the main reason is that it's a common fact or belief, and it's also known that we have to melt the material when we are spraying it. And when we are melting a nanostructured material, then we are losing the nanostructure. And the melt don't have a memory in this sense, and that's a critical issue when we're trying to produce these nanostructured coatings by thermal spraying. And actually, if we look at conventionally thermal sprayed coatings, like here below is an example of a chromia coating, a conventional plasma sprayed, and it has already a nanostructure, because when cooling down the molten droplets, there is a very high cooling rate and the nucleation of small crystals, or there might be some chemical reactions also which result in these nanoparticles in the sun is shining so brightly that perhaps you are not really seeing the pictures, but after dark winter we can perhaps accept that. So thermal spraying is a wide, there is a lot of different kinds of thermal spray technologies, and spraying itself is a quite complicated process, because we try to produce from powder by melting coatings, and we have to obtain also the good properties. So we normally have a powder feedstock. Then we have an energy source, flame, arc, plasma, or we can use also kinetic energy. Then we melt the material. Traditionally, at least, we melt it, but now we have to consider some options not to melt it completely. And then coating is formed on the surface of the substrate when the droplets are solidified to the surface. And actually, although there is a lot of droplets, they all, when they hit the surface, they solidify before the next drop is coming on the top of that. And it means that we get the so-called splats, and they form then the layered coating, as I describe a little bit later. And we have a lot of parameters which we have to control in this process. We have different techniques, as mentioned, in thermal spraying, but now the more interesting are plasma spraying, and then these high velocity processes, and nowadays these high velocity oxyfuel spraying. Let's see the plasma spraying a little bit more detail, and here is a typical plasma gun. Plasma is formed here inside the gun due to electric arcs, and then there is a plasma plume, and then we feed the powder here into the plume radially, but we have nowadays also guns having axial powder feeding. And there is a quite complicated situation in this plasma plume when we have this high velocity gas flow or plasma flow, and then we feed these particles and mixing air and other things to that, and that makes these difficulties for controlling the structure in atomic and molecular level. We are only controlling it mainly in particle level. Here you see the typical ceramic coating plasma sprayed alumina, and here you see those molten droplets on the surface, and if we polish the surface and looking again then we see that there is pores, and then cracks in this ceramic coating. These are typical features in the ceramic coatings, and this porosity here can be few percent up to 10% in these plasma sprayed coatings, and it's also open porosity from the surface down to the substrate. And then if you look this cross section, then we see these layers which are formed by these separate splats. If you look at time scales here, when we form the coating, then the droplet will flatten on the surface very fast normally, or short time, and then there is a solidification and the crystallization, and here we have these small crystals formed on the splat, and then it's solidified after this period, and the next droplet is coming here, and then we get we call it, there is a passes when the plasma gun is going over here, and forming a coating gradually, and then what we get is finally this kind of structure. In conventional plasma spraying, we have to granulate the powder, or we have to crush it by crushing to the size of, let's say, the 20 to 60 micrometer, and that gives dimensions for the droplet. And typically the coating thicknesses are, for these ceramic coatings, they are a few hundred micrometer up to millimeters. When we look in this and these fine structured coatings, we come in a little detail to that. But in HOVF spraying, which is based on burning the fuel, the temperature is somewhat lower or much lower than in plasma spraying. It can be in plasma spraying 10,000 or even more degrees, but in burning the fuels, it's typically below 3,000 degrees. And in that case, when we have a ceramic powders, we need finer fractions when we are spraying, but what we get actually is then we get the higher particle velocities. In plasma spraying, typical velocities are 200 to 400 meters per second, and in HOVF they are 800 to 1,000 or even more in certain cases, the particle speeds or velocities. You know, what we have to do when we try to produce nano-sized coatings, and as I already said, that we have to avoid the melting of the material, and we have several approaches, and from material point of view, the approaches are largely studied at this moment is that we made the nanostructured agglomerated ceramic powders, and then we are only partially melting that powder to retain a nanostructure, but then we have actually a composite structure where we have this non-melted part and then the melted part. There is typically quite a lot studied these alumina-based coatings, titania, zirconia coatings, and there is already commercially available materials from several companies for these compositions. But of course in scientific literature there is a lot of homemade powders also, and which differ somewhat with this main stream. So what we get actually then, we have to agglomerate or granulate actually the powder again in order to be able to transfer it in the thermal spray equipment to get the powder fluidicity high enough, because these nano-sized powders, they are not flowing really, and they're causing problems in spraying. And what we get then is, as I said, we have a bimodal structure or partially melted, and then these so-called nanozones in the structure, and then we have this structure which is totally melted as typically in thermal spraying. And from properties point of view, there is then found that there is an optimum amount of these nanozones actually, which give the best wear resistance, for example, and then this optimum amount depends then on the material basis what is in the coating. The problem here is, as you can imagine, then we have to use high temperatures, but not to melt totally the material. And that means that we have to have a careful control of the spray parameters. And then one which helps in this is we have online diagnostics of the particle temperature, so we can control it. But in certain cases, we can even exceed the melting point of the material if we have a short dwell time of the particle in this hot zone, so it is not totally melted during the spraying. But if this all is optimized properly, we can get the properties, not so much increase in the hardness. It's typically a little bit higher or a little bit lower or the same as in conventional ceramic coatings. But what we get improved is toughness. Ductility of the coatings is improved. So it means that the crack propagation resistance in the coating is increased. And that is normally measured by this Vickers indentation fracture toughness measurement system, because otherwise it's quite difficult to measure the toughness of this kind of coatings. And it's explained that that improvement in toughness is due to crack arresting zones, or crack arresting by these nano zones which are in the coating in different places. And then there is also found an enhanced interlaminar strength in these coatings. Also, bond strength to the substrate is enhanced in these coatings. What is also found, which is not so typical for these ceramic coatings, that they have some plasticity, at least some plasticity in the, and this has been seen, for example, in wear testing when we're looking the wear scarves on the surface, and we see that after wear the surface is more smooth as compared to the same kind of coating which is conventionally sprayed and after the same wear procedure. So we have this titania coating here, which is HOV straight from this nanostructured titania, and here is a conventional titanium surface. And in this conventional material, we have a detachment of the material from the surface, cracks, delamination of the lamellas, and so on. And what kind of improvements people have found in these coatings after sprayed by plasma spraying, and here are the coatings, and we see that there has been in optimized conditions as compared to the conventional coatings sprayed with the same system and tested in the same way, that there is a reduction in abrasion and sliding wear levels in these materials. There is a quite considerable decrease. And if we have these high velocity sprayed coatings, we can even get an even higher improvement or further improvement to these wear properties. Here is two types of coatings, titania and this alumina titania. And then there is even more higher reduction as compared to the plasma sprayed coating. And it's explained or found when they study the materials and coatings that it's due to the improved homogeneity and the toughness of the coatings. And for example, if it is studied by Weibull statistics, the hardness measurements, and we get a much higher Weibull modulus, and which means that the homogeneity is much improved in this kind of coatings. A little bit of these biomedical applications, and as perhaps most of you have found, and if it also often referred in the literature, that this Webster's group, they found that on ceramic surface, when we have a certain nanostructure or nanotexture on the surface, there is we have enhanced biocompatibility with the osteoblast cells, and it has been found that there is a higher cell reproduction and also improved adhesion of the cells. And that's really explained by this nanotexture or nano-roughness of the surface. And it is said that found that there is certain adhesion proteins which are attached to the surface, and they are anchoring these osteoblast cells to the surface. And these adhesion proteins, they are immediately formed on the surface when the implant is operated, and then the osteoblast cells, they found then these adhesion proteins on the surface. And these proteins, they have also a nano-sized structure, and it's compatible with these structures. So in this case, these nanozones, which we have not only inside the material but also partly on the surface, then they are causing this in thermally sprayed coatings, and then we have a perfect match here. These nanozones, they improve the properties, mechanical properties, and then enhance the biocompatibility. So if you look these important bioceramic coatings, hydroxyapatite is commonly used in implants, and in that case, this nano coating actually is not so much improving the mechanical properties, and it's probably due to the inherent weakness of the material. And it's been found that hydroxyapatite phase content, its crystallinity, and it's affecting more to the cell adhesion. But nowadays there is also a lot studied this titania as a possible replacement for this hydroxyapatite, because it's giving a much higher mechanical properties, and it's also found to have this biocompatibility, and it's now widely tested for this application also in a nanostructured coating. Okay, the next nanostructured or approach to make nanostructured coatings by thermal spraying is a concept where we spray glassy or amorphous material, and then it's heat treated to certain nano size grains and nanostructure. So it needs a post-treatment to crystallize the nanostructure, control the structure. It's also studied for bulk nanocomposites, for example, in those cases where we have a high yield thermal or plasma spray system like this water stabilized plasma, which is producing material several kilograms per hour. And I'm a doubt a little bit with this concept with the coatings, because when we heat treating then the coating after spraying, the substrates should also stand or be resistant against these temperatures, which are normally quite high, 800, 900 degrees, and then we have to control the atmosphere if we don't want to oxidize this. And if you're looking at large applications, what we are interested in paper and pulp industries, for example, a 10-meter long rolls, 1.5 meter diameter, it's very difficult actually to heat treat those, and they also cause a lot of deformation perhaps, and that's not a concept for that kind of components. Okay, then the process approaches to nanostructured coatings. There is these systems where we're spraying nanoparticle suspensions with these high velocity processes, and Professor Kado's group in Stuttgart has been developing this high velocity suspension flame spraying system, and there will be something during this course also in this modeling part, I suppose. And then the other concepts which are of interest are chemical synthesis during the spraying. They are not, let's say, conventional in thermal spraying society, but chemical synthesis has been used quite long time, also in the connection of the spraying. Or then perhaps we have possibilities when we have a cooler heat sources, but very high kinetic energy, so that there will be a plastic deformation with the nanoparticles or matrix which contain the nanoparticles. Suspension spraying, I perhaps skip this because there is not so much time left. So if we then look this chemical synthesis during spraying, and it has its background actually so chemical vapor deposition processing of the thin layer coatings. So we combine chemical reaction to form these materials to the spraying system. And why I like this concept is that we can have atmospheric processes which are interesting for the large area applications. There is different techniques existing already. There is spray pyrolysis where the precursors evaporate when they are approaching the hot substrate, and this been widely used in glass industries. There is then a concept where we use a thermal spray gun, flame spraying gun, and we feed a liquid without particles into the gun. So the precursors are fed to the hot zone in the flame. And there is also some combustion CVD processes which are not so common, but they are also studied and developed for for certain applications where the solvent is a fuel and there is no additional fuel in this case. Here is some reactors, for example, for oxide nanoparticles, and these processes are used actually in very large industrial applications. For example, the carbon soot is industrially produced, these kind of things. Our concept is close to this one, where we have a multi-annulus co-flow burner, where we have different channels for the reactants or precursors, and then some inert gases which are separating them before they are intended to meet each other outside the gun. If they meet on the surface of the gun, then we have serious problems in clocking and closing the gun. Okay, this way. So we have a system where we feed hydrogen, oxygen to the system, and then precursors. In the silica case, we have Theos, and get then reaction happening here in homogeneous nucleation in the gas phase and get the particles. And this has been used quite a long time for producing particles and nanoparticles. But we can use it perhaps also, or we have tested a bit using it to form a coating when we collect this coating at a certain part of the flame. So we heat the substrate and get a chemical reaction like chemical vapor deposition, and then we form the coating on the surface. My background is in the coating business, and I'm always a little bit let's say afraid to have these nanoparticles before the surface. When you have them, then you don't have any possibility to make a good coating anymore. So if you want to make it chemically, by these chemical reactions, those reactions should happen heterogeneously, catalyzed on the surface, and then you have a coating. But if you get these nanoparticles, they are heavily agglomerated normally, and then we have a loose so-called soot, what we get. Here is what happens there in the gas phase processes, and if we collect them on the surfaces, then the problem is that the particles start to grow this hot area, and then that will be a problem in the nanomaterial production. So we have to optimize the place where we collect those particles, and if we get a really CVD type process, then we get only coating, not the particles, and that would be optimum, but it's difficult to obtain those conditions. And in CVD process, then we have a lot of process steps here, from the gas flow to the surface, diffusion zone here, adhesion to the surface, chemical reaction, and desorption from the surface, and that all should happen. But normally, when we obtain these nanoparticles, then they are homogeneously nucleated in the gas flow, and then we had those processes seen in the previous slide. What we have now doing or done, we have scaled up this system for the flame spraying gun, and here it is without the collection system, but we can produce nanoparticles mainly, but we have also tested the nano coatings. And this is a good process to produce these particles with different architectures, and what we have studied, alumina-zirconia, iron nanoparticles, and then titania, silver nanoparticles. There is options to have different structures to the particles, and here are those which are possible, and for this alumina-zirconia iron nanoparticles process is described here. And what we get a powder with crystalline zirconia tetragonal and having a small crystallite size. Alumina is typically amorphous, and if we add iron there, then it's so small that it's not found in this X-ray, but XPS it can be found, and also by mass power spectroscopy. And here are pictures of the particles what has been obtained by this process, and they are further used to grow the carbon nanotubes. Here is an example of the massive growth of the tubes. Here is a powder before the heat treatment to grow the carbon nanotubes. After it looks black as seen here, and it's also confirmed by Raman spectroscopy to have a nanotubes structure. The problem, of course, in this case is that it's when we have this agglomerated or aggregated powder and the carbon nanotubes are everywhere there, and then we've been discussing how to compact this material to the solid ceramics so that we have carbon nanotubes mixed with composite nanoparticles, and that's a big challenge, and if somebody has a good advice how to do it, then we are happy to hear it. But we are also looking to get it a little more organized way, but next time perhaps I can tell about that. Then titania coating is also interesting from these photocatalytic properties, antibacterial properties, and easy to clean or self-cleaning properties. And it can be also done by this liquid flame spraying. Even you can spray glass surfaces. There is an industrial company in Finland offering this kind of process. You can control the anatase rutile ratio by distance and temperature. And what we have also done, because photocatalytic coating is antibacterial only in this UV light, we have made a mixture where we have a silver and titanium nanoparticles, and hope to get the coating to be antibacterial also when we don't have a UV light. And here is this anatase particles. They are small ones, and there is some droplets formed the rutile particles, and then silver inside the material. And the structure is where we have this titania, and then we have these metallic nanoparticles on the surface of that. And that photocatalytic activity has been tested by degradation of the stearic acid in UV light. And in this case, we have there has been also the powder on the surface, but we have cleaned the powder off, and then we have a real attached layer on the surface, and that's also a photocatalytic. And it can be done with one-step process where we at the same time produce silver nanoparticles and ceramic nanoparticles, and it works and gives good properties. We have studied quite a lot with the microbiologists this antibacterial behavior, and here is one bacteria which is living in a paper machine. It's Deinococcus geothermalis, and the name says that it's normally found in the hot springs in earth, but somehow it has found its way to the paper machine, and the reason is that in paper machine the temperature is also 40 to 60 degrees in the water, and it has found that it's a good place to live, and somebody has said that it's the fourth eldest living organism in the in the earth. But it looks like this. Here it is wealthy, and it's attached. Normally that attached to the stainless steel surface, but here it is on titanium surface. Normally in the water flow it's a totally spherical, but then when on the surface it has these organelles will attach to the surface and to each other. And then we have tested these coatings then in the UV light, and this below you can see that they are not anymore healthy, and that they also tested that it's mostly dead organic residue, all of those. And here is an example of these flame thread coatings, and in dark with this one-step process, silver is decreasing the cell number, and then when we have a UV light, then there is no living organism anymore. So this liquid flame spraying is a versatile technique to make different nanoparticles. As I said, that they are normally heavily agglomerated, but there is also concepts that you can spray it also to the liquid film on the drum and then collect to the liquid, so you can make them separately, and there is a companies also using that technique. There is several benefits, and I have already mostly mentioned them, so I say only a few words on laser processing at the end of the surfaces. We have nowadays a lot of different kind of lasers available for material processing, and they are developed. There is a lot of development work done with the lasers, and so every week or every month there is a new versions coming out of different advanced laser concepts. But they are not developed for materials processing, and the point is that in materials processing we have to be ready to adapt those for our processing when they come available, and follow up the development, what happens in that field. There is now also these pulse lasers having a picosecond or nanosecond pulses, and they make possible the processing of materials or machining, for example, without any significant heat effects. And this is mostly, of course, for polymeric materials. It's good, but it can be also used for ceramic processing. So we have a lot of options. Now you realize that we are approaching a peak of this fiction part of my presentation. But we can use these lasers. Laser is a very controllable heat source for material processing. So we can first use this for firing or sintering pre-deposit layers on the substrate. And when we have a nanoparticles, nanoslurries, we can make pre-deposit those on the surface and then laser firing, laser sinter them without melting the materials. This gives an option of, for example, to make these bioactive nano-patterned surfaces. And the other is we can use soil cell film, for example, and heat treat it by biolaser. What we get the nanostructured surfaces for tribological purposes, for biomaterials, and additional functionality, which includes everything, good properties you can produce. And it can be also used layered manufacturing, like in this rapid prototyping type systems, but produce ceramic materials. And it can also, they can be used for laser, micro, and nano patterning. Laser remelting the thermally sprayed coatings has been studied for a long time. And here is an example with a high power laser. In this case, we have melted the TPC coating, and you can see the melted area of the coating. And this is a typical feature if you melt the thermally sprayed coating. Then there is this columnar solidification, columnar grains, and here is an interface between the laser processed part and the thermal sprayed part. And what you see also, there is normally found a lot of porosity in this interface. But we have been considering how to laser sinter nano composite powders as a coating, because within this nanocare project, for example, there is such a powders produced for example, alumina-nickel powders. And it's not so easy to find the way how to make a coating of that material having this improved hardness, what you have heard or you will have here during this course. And one concept what we've been thinking is that we first use a thermally sprayed coating as an intermediate, so-called bond coating actually for this material, and then pre-deposit this powder layer on the surface of that, and then try to laser sinter it to have a maximum density and good properties. And here is now an example of those. This is not yet a totally nanostructured powder, but we have tried to demonstrate it. And here is a densified alumina surface. We have densified it by this laser process. Now you can imagine then the solution to be that we have a substrate, we have a thermal sprayed coating, so-called low modulus layer here, and then we have this nano coating on the top of it, having these nano dispersions inside of it. It's not so easy to make it by PowerPoint, but it's much more difficult to make it in practical or real life when you try to realize this concept. But anyway, that we believe that it is one way how to do it, and if you have a success, it's good. And even if you are not able to make it the nano dispersions here, we are looking also the concept where we use higher metallic inclusions of dispersions in the thermally sprayed coatings to densify it, having, for example, in the case of alumina, having a much better thermal shock resistance and having the density or dense layer against the corrosion, and so there is a different scales what can be tested, and it's normally so that if you are not managed to do what you want to do, you'd get something else what is still useful, and we are trying to use this concept, and if we don't succeed in this concept, but perhaps we succeed then in this micro world to improve these thermally sprayed coatings. Here is also an example of a laser patterned titania coating. This made in this 515 nanometer laser pulse laser fiber system, and here is an area which has been treated, and here is a higher magnification, and the laser beam has been this way and then this way, and there is a little bit deeper holes here because it has a double time of the laser activity on the laser treatment on it. But what is interesting also here, you can see that we have a micro pattern, but we have also a nano structure on these. And now we try to benefit or test it further if we have a nano micro composite structure produced by this laser processing. So that was something to think about or appetize for you to this laser processing, and there is a big challenges, but be careful, lasers are here already, and they are coming as practical tools. So I want to thank my researchers contributing to this presentation, and here is our university campus main building. This is a very rare situation nowadays due to this greenhouse effect. We have only few weeks snow even in Finland at this moment. But thank you for your attention.